Greetings. In my previous video, we had a look at this block diagram that pretty much summarizes the operation, the functionality of my 10 gig transceiving system. So this is great at the RF level, but what about the power distribution of this thing? And also the sequencing, because we have to transition from receive to transmit and back into receive in a certain order. So these are two parts, power and sequencing, that we have to look at. Let's start with power. So this is a block diagram of the power distribution and power consumption of the entire system. So there are three phases or functions that we need to cover in the power distribution. The first one is the always on. As soon as we apply 12 volts plus minus to the system, these sections, these parts of the system will always be on. And then we have the receive on and the transmit on sections. So we need to plan for the power of these three sections. So I start with a 12 volt battery, and of course I've added a fuse. A 5 amp fuse will be sufficient. It can be a fast acting fuse and that'll be fine. And then we fan out the 12 volts to the different functions. We will eventually have a TR sequencer, so it'll be a board that will receive the 12 volts and derive local voltages to make the sequencing work. So that's always on. The currents that you see written here are actually currents that I individually measured on the blocks. So I'm pretty confident that these will add up and the final current drawn will be close to this. Another block that always receives the 12 volts is the oscillator, the OCXO. We want to warm it up before we start operating. It will have to be on for at least a couple of minutes prior to operating. So this is another always on block. That's the 12 volts directly to some blocks. Now, one important voltage in my system is the plus 8 volt regulated voltage, because it will get split into the three phases: always on, transmit, and receive. And that's what's happening here. We have the always on the synthesizer board. So 8 volts is okay. It has an onboard 3.3 volt regulator. So feeding 12 volts would have pushed it a lot as far as the power dissipation, but 8 volts is okay. And then we also have the tripler board. So essentially the LO will be always on. Tripler board will be always on. And these are the currents that these blocks will draw. There's another always on voltage, and it's the minus 5 volt required for the power amplifier. That minus 5 is very low current, maximum 10 milliamps. And there's no real value in putting it on only on TX since the current drawn is so little. So I've decided to tie it directly to the plus 8 volt always on. It will supply minus 5 to the amplifier, but that's fine. There's no plus 10.5, so the amp is still in idle. Okay, so now we split into transmit and receive. So the receive portion draws plus 8. It will be through a switch on the sequencer, some sort of relay, either mechanical or solid state. And this will turn on only when the whole system is ready to receive, meaning also that the IF rig is hooked up to the system. So the currents are sent to the transverter board for the receive portion only, to the attenuator for 144 megahertz bypass of the 30 dB attenuator. That's a little box that I built. And also to the low noise amplifier, because we're in receive, we want to preamplify the signal we get from the antenna. So these are on receive. Now if we switch to the transmit, we still provide plus 8 volt now through a transmit switch, same as the receive switch, but they will alternate in on-off, of course. And that plus 8 transmit will be sent to the transmit portion of the transverter board. And then for transmitting, there's another big part, and it is the amplifier, the power amplifier itself. So the 12 volt is taken directly from the 12 volt bus, and it goes through a beefy 10 volt 10.5 volt buck regulator that will supply plus 10.5 regulated at more than 2 amps. But that buck regulator has a control pin to shut it off. And that's going to be the sequencer's job to turn on the buck regulator only when we are in transmit mode. So there's no switch required. That's a nice thing about this buck regulator board. It's just a control signal that's kept grounded to shut off the buck regulator. So that will provide the plus 10.5. We mentioned minus 5 is already there. So we are in TX. The only transmit part that's missing is the transmit receive relay on the antenna. And it's a 24 volt relay. So I've decided to take it directly from the 12 volts through a boost converter, and I've tested the switch, and 20 volts is more than enough for the relay to operate, and it reduces the current consumption. Instead of 24 or 28, 20 is fine, and it's still 200 milliamps at 12 volts, so it's not negligible. And of course, for these two regulators, and even this one, they are noisy because they're switching supplies, so some additional filtering will be required near these switchers. So that is the power distribution. Now, in terms of current consumption on the 12 volts, if we take all these currents, considering some are switching, some are linear regulators, we come up with, when the radio is disconnected but the system is powered on, for the first minute or so, it will be 1 amp, and it's basically these circuits that are on, and the OCXO that draws a lot of current to heat up its temperature chamber. But after a minute or two, the chamber is heated up, mostly, and the current falls down to 550 milliamps. When we connect up the radio, the IF radio, to the system, it turns on the receive chain. And again, if we power it up directly with the receive chain turned on, the system will draw 1.45 amps. And then once warmed up, in receive, 830 milliamps, and in transmit, 3.25 amps. And of course, that 325 and 830 does not include the IF rig itself, the 144 radio. So you can see that the 5 amp fuse I've settled on, and that excludes the supply to the IF radio. 5 amp is good enough for a 3.3, 3.4, 3.5 amp current in transmit. So there you have it. And of course, like I mentioned earlier, now the next step is to design a TR sequencer to control these supplies in the proper order so that we don't blow up anything, like transmitting into an open relay. So the relay has not done its job of switching yet. So this is a job of a sequencer, and it will be the subject of my next video. So until then, 7-3.